Hello everyone, I'm Wanrong from Harvard University. Today I'll be telling you about our work on concurrent composition theorems for differential privacy. So let me start with a quick recap of the basic definition of differential privacy. Informally, it ensures that one person's data won't change the distribution of an algorithm's output too much. And this in turn can limit the amount of information leakage of an individual from the algorithm's output. And this information leakage is quantified by a privacy loss parameter epsilon. And formally, we see an algorithm is epsilon differentially private if for all pairs of neighboring datasets then differ in only one arbitrary person's data. The distribution over the algorithm's output on these two neighboring datasets must be close in this multiplicative sense. And the fundamental property of differential privacy is composition, which is the central feature in today's talk. It studies this problem. Suppose you ran k differentially private algorithms on the same dataset and released all of their results. And how private is this as a whole? So the basic composition theorem tells us if each algorithm satisfies the pure DP guarantee with privacy loss parameter epsilon, then the overall privacy loss is bounded by k times epsilon. And this property is especially useful from the algorithm design perspective. And it allows us to safely combine k algorithms to build a more complex algorithm. And you just have to pay this linear rate of privacy loss, k times epsilon. And the natural question is how to improve this linear rate. So recently, there's a number of variants of differential privacy has been defined based on other closeness measures, such as the epsilon delta DP, concentrated DP, Rene DP, and FDP. So why do we care about these different variants of DP? The main reason is that their composition properties are better. For example, with epsilon delta DP, we have the Vance composition theorem. So with this, the privacy loss grows sublinearly as the number of computations. So among all these notions, this FDP can characterize lossless composition property. And in fact, we use it to do privacy accounting for DPSGD, which is a state-of-art DP optimizer in deep learning. And this notion is very general. For example, it captures this epsilon delta DP as a special case. But all existing composition theorems based on this DP variance are only for non-interactive mechanisms that release query answers in one shot. But what if we consider interactive mechanisms and what composition guarantee we can get? So let me start with describing a non-interactive mechanism versus interactive mechanism. So for non-interactive mechanism, the analyst sends one query and get back one answer. This is a single-shot mechanism, and we call it non-interactive. For example, a non-static mechanism such as Laplace mechanism is a single-shot mechanism. But this is not enough for many practical problems. For example, in a machine learning pipeline, we might want to do feature selection first, and then train a machine learning model based on the selected features. So we need to introduce interactive mechanism, which allows us to ask an adaptive sequence of queries about the dataset. And this is very useful and needed for many practical problems. And like here, we're doing multiple rounds of computations. For one round, this is a non-interactive mechanism. And for the whole procedure, we call it as an interactive mechanism. So the goal here is a whole mechanism instead of one query. And importantly, this sequence of queries can be determined dynamically. And also, this mechanism responds to the query in a randomized and stateful manner. So you can actually view the adaptive composition of non-interactive mechanisms as an instance of an interactive mechanism. But the interactive mechanism is more general. For example, there are some useful primitives in DP. They are interactive, but they are not analyzed through adaptive composition of non-interactive mechanisms. For example, the sparse vector technique and private multiplicative weights. To formally define interactive mechanism, we view the mechanism as a party in an interactive protocol, interacting with a possibly adversarial analyst. So in an interactive protocol, each party has its own private input and a random coin, and the function then takes in the history and produces a message to send to the other party. So in the setting of DP, we have the adversary as a party, but it does not have an input, and only the DP mechanism has a private input as a dataset. And the random coin for each party characterizes the randomness in producing a query or a differentially private answer. And here we only care about the view of the adversary. So it consists of all the messages the adversary received in the protocol. And with this notation, interactive DP is defined by asking for the views of an adversary on any neighboring datasets, satisfying the same absolute closeness notion as before. And again, this closeness notion can be generalized to other closeness measure. So now we consider composing interactive mechanism. So I'm gonna use this example to explain where things can be different. As a Harvard employee, I can choose between two health insurance systems each year. And last year, I was using Blue Cross Blue Shield. And this year, I decided I want to switch to Harvard Healthcare. So they both have my medical information, and this is highly sensitive. So suppose there's a malicious adversary. They first query Blue Cross Blue Shield, and then query Harvard Healthcare. And in this case, everything is strictly sequential, and each mechanism is executed independently. So it's easy to see we can extend the previous composition theorems to account for the total privacy loss in this case. But what if a malicious adversary queries the two systems concurrently? For example, after getting some answers, the adversary uses this information to query Blue Cross Blue Shield, and then after getting back the answer, and again use this answer to query the Harvard Healthcare. So the query sent to Harvard medical system may depend on answer received from Blue Cross Blue Shield. So it's not clear if the adversary can break my privacy guarantee because of this correlation. So we are currently lacking analysis to account for the total privacy loss under the concurrent composition setting. So in summary, there are two cases when composing interactive mechanisms. The first case is a sequential composition, and the previous proof of non-interactive mechanisms are easily extendable. So the interesting case is the concurrent composition. And this setting is well studied in the cryptography literature, and it's often more subtle than the sequential composition setting. For example, there's a famous result showing that standard zero-knowledge protocols are no longer zero-knowledge when a single prover is involved in multiple zero-knowledge proofs. So the question for us is, for the setting of differential privacy, will concurrent composition make things worse than sequential composition? And I want to talk about another motivation, which is the DP software systems. So I'm going to use our Harvard OpenDP as an example. Even though we have already deployed interactive measurement to do interactive mechanisms, we had to force all interactive mechanisms running strictly sequential because we only have theorems to back for that case. So we had to build an internal tracking system to track the completion of each interactive mechanisms, which means we cannot allow multiple people to set up servers at the same time. So this is so unnatural, and we wish to avoid that. And ideally, we wish to have a natural interface that allows us to set up servers at any time and in arbitrary order. So the concurrent composition is first studied for differential privacy in Vadhan and Wang 2021. And in this setting, an adversary can arbitrarily interleave its queries to different mechanisms. And those queries might be correlated and depend on answer received from other mechanisms. So it's not clear if the adversary can run any concurrent attack to break the overall privacy guarantee. So we wish to provide a probable guarantee to account for the total privacy loss in such a system. And the only previous paper shows that the composition theorems for non-interactive pure DP mechanisms extend to the concurrent composition of interactive pure DP mechanisms, which means we can extend this k times epsilon, this linear rate in this block. But for epsilon delta dp, which is more commonly used in practice, they only show that the concurrent composition bound is this. And this bound is even suboptimal to basic composition because in addition to this k times epsilon, we have an additional slack term. And for DP expert, you may notice that this bound is actually group privacy-like bound. So it left us an open question: can every composition theorem for non-interactive mechanisms extend to concurrent composition of interactive mechanisms for standard variants of DP? And in our work, we answer this question by showing that any composition theorem for non-interactive epsilon delta DP mechanisms extend to concurrent composition for interactive epsilon delta DP mechanisms, which means we can still get this sublinear rate for interactive mechanisms. And similarly, we also show the same analog for theorem 1 also holds for this more general relaxation of FDP. And in particular, theorem 1 follows directly from theorem 2 because FDP captures this epsilon delta dp as a special case. So in the rest of this talk, I'm gonna focus on FDP. So basically, our results tells us the concurrent composition will not make things worse. We can achieve the same bound of privacy loss as in the sequential composition case. So in the next few slides, I'll talk about how to prove this result. So our proof strategy is to show a reduction from interactive mechanisms to non-interactive mechanisms. And we have this reduction theorem. It says for a given interactive mechanism M, for every fixed pair of neighboring datasets, X and X prime, there exists a canonical non-interactive mechanism N, and a post-processing function T, such that the view of the adversary interacting with M is equivalent to the view of the adversary interacting with this post-processing function T, then takes in N of X as the input. So basically, it says that for a fixed pair of neighboring datasets, X and X prime, every interactive FDP mechanism can be simulated perfectly by an interactive post-processing of a canonical non-interactive mechanism. And here, this post-processing function T depends on M and also this fixed pair of neighboring datasets. And it takes this N of X as an input, and it does not take the dataset as the input. And this T interacts with the adversary A just as M does. This reduction theorem is very surprising because this non-interactive mechanism N, it produces the answer without knowing all the queries from the adversary. To understand this result, let's look at some special cases. A direct corollary is that every epsilon delta interactive mechanism can be simulated by the epsilon delta randomized response. And this can be obtained by combining the reduction theorem in KOV 15 for non-interactive epsilon delta dp. And also this corollary is independently obtained in Liu 2022. For pure DP, the previous paper also shows that every interactive mechanism can be simulated by the epsilon randomized response. So this reduction theorem implies that to analyze the concurrent composition of interactive mechanism M1 to Mk, it's equivalent to consider the concurrent composition of this post-processing that takes this canonical non-interactive mechanisms as an input. And because differential privacy is robust to post-processing, which means we only need to consider the composition of these canonical non-interactive mechanisms. And as a result, composition theorems for non-interactive mechanisms extend to concurrent composition of interactive FDP mechanisms. I want to emphasize that the first step is where all the hard work is. And the main idea of our proof strategy is that even though the definition of differential privacy requires us to consider all neighboring datasets, but when we analyze composition property, it is sufficient to consider the fixed pair of neighboring datasets, and you just have to analyze this one canonical non-interactive mechanism. And next, I'll talk about the proof sketch of our reduction theorem. Let me briefly introduce FDP. FDP is a generalization of epsilon delta dp based on the hypothesis testing interpretation. So here, differential privacy attempts to measure the difficulty of distinguishing two neighboring datasets based on the output of a mechanism. So specifically, an adversary considered this hypothesis testing problem, where this H0 is the dataset is X, and the H1 is the dataset is X prime. And then for given rejection rule, the type 1 error is the probability of rejecting H0 when H0 is true. And then the type 2 error is the probability of failing to reject H0 when H1 is true. And with that, we can define the trade-off function as a best type 2 error given the level of the type 1 error. And this trade-off function characterizes the optimal boundary of the achievable and unachievable regions of these errors. Then we can say an algorithm is FDP if for all pairs of neighboring datasets, the trade-off function between mx and mx prime is greater than a target trade-off function f. So which means the best type 2 error is at least f of alpha. So this FDP allows the full trade-off between type 1 and type 2 errors by this target trade-off function f. And a larger trade-off function implies stronger privacy guarantee. And this is in the opposite of the traditional epsilon DP. So our proof relies on two properties of FDP. We first show a novel coupling property of FDP. And it says, suppose we have two pairs of random variables, such that the trade-off function between the two pairs are greater than this target trade-off function f. Then there exists a coupling of these two pairs, such that the trade-off function between the two pairs of couplings is also greater than f. So here, a coupling of random variables x0 and x1 is any random vector y0 and y1, such that the marginal distribution are identically distributed to x0 and x1. And subjecting to this constraint, this y0 and y1 can be arbitrarily correlated. And I want to emphasize allowing this correlation is very critical. For example, for the case of epsilon delta dp, if we keep those two pairs of random variables independent, then we will just have this group privacy-like bound. And another property we show is this chain rule. And this terminology chain rule is by analog with the standard chain rule for the KR divergence. So here for the KR divergence, we have like fixing x and x prime, we can calculate the KR divergence for arbitrary y and y prime as a function of this. So similarly, the chain rule for the trade-off function says that there exists a continuous momentum function chain rule such that the trade-off function between the xy and x prime y prime can be determined by a collection of trade-off functions between y and y prime conditioned on x and x prime through this chain rule function. So this is a very nice property because if we work with the epsilon delta dp definition directly, it does not have this chain rule property because no pairs of epsilon delta can exactly capture the closeness of xy and x prime y prime, given a collection of this epsilon delta then characterize the closeness of y and y prime given x. And working with this general FDP allows us to capture a complete characterization of the privacy. So now I'll show you how to use the two properties to prove our reduction theorem. So let's briefly recall the reduction theorem here. So our proof strategy is to apply induction on the number of messages exchanged. So to reduce k rounds of interactions to k-1, we consider a subsequent interaction conditioned on the first message. So depending on whether the first message is sent from the mechanism N, mechanism M, or the adversary, we consider two cases. The first case is the adversary sends the first query Q to the mechanism. So fixing Q, we consider subsequent interaction in MQ. So by induction, this part can be simulated by post-processing of a non-interactive FDP mechanism NQ. And then we're gonna use the coupling property. We're coupling all possible pairs of NQ on X and X prime on all the values of Q, which is all possible values of the first query. And I should mention that we stated the coupling property for two random variables, but it also extends to a finite number of random variables by induction argument. And then following the coupling property, the overall trade-off function is still greater than f. For the other case, where the mechanism sends the first query to the adversary. So suppose the subsequent mechanism conditioned on this first message A is FADP. And by induction, this MA can be simulated by a post-processing of a non-interactive mechanism, FADP mechanism NA. Then through this chain rule function on all possible first message A, the non-interactive mechanism constructed as ANA also satisfy FDP. And this non-interactive mechanism sends AY to the post-processing function T. And this function simply sends A as a first message to the adversary, and then simulate the rest of the message by TA of Y. So we also show that the reduction theorem holds for this case. So I'd like to conclude the talk here. The main takeaway is that we show concurrent composition theorems. And what can we do with that? So first, it allows analysts to conduct concurrent analysis on sharing data without worrying about someone may access all the servers to play around some stuff. And second, it can enable full interactivity in DP systems. So we no longer have to put sequential constraints. Now we can split our budget in multiple parts and do arbitrary things in each part in whatever order we want. And we are happy about this new feature of interactivity. And this work is currently being integrated into OpenDP, and it also affects all the DP software systems. And thank you for your attention. And for more details, please check our paper online.